So let's take a look at solutions for solutions are homogeneous mixtures. They could be gaseous solutions like air. Air is a homogeneous mixture of nitrogen and oxygen and some other gases. Liquid solution, hydrochloric acid, solid solutions, etc. Or solid solutions are called alloys. Alloys would be like stainless steel or steel. Steel's iron mixed with other elements, brass, etc. Those are solid solutions. There are lots of different compositions of alloys, depending on how much you vary particular components that make it up. These solutions, the particles, this first particle we call solute. The solute doesn't settle down. That's different than a suspension, like muddy water. Muddy water we wouldn't call a solution. One, you can't see through it. Two, eventually the mud will settle. That's different. Solutions have variable compositions, like all mixtures do. Compounds have fixed compositions. Solutions are mixtures, so mixtures have variable compositions. As the composition varies, the properties will vary, like sweetness, concentration. A solution has two major components, the solute and the solvent. We could have multiple solutes, like in air. Solvent's usually the major component, like water would be a major component. Solute would be what you dissolve in the water. And so solute and solvent. If you add up the solute plus the solvent, we get the solution. So here we can see. The solvent would be water, the major component. Here the solute is going to be, this looks like copper 2 chloride. This is a blue solid here. Chlorides are soluble except for silver, lead, and mercury, so this should dissolve. And so the solute dissolves. So they took a couple of scoops of this dissolved in water. You can see the blue color. The blue color is due to the copper 2 ions in water. And chlorides are colorless. These would be the chlorides here. What happens is, this is positive, so the negative end of the water molecules, water is polar. So the negative end, the oxygen ends, point towards there. This is called a hydration sphere. So what we get, we end up with hydrated or solvated ions, water being the solvent here. Chloride, the hydrogen ends point towards it. It turns out that these spheres of hydration help stabilize the ions with lot. So we think about the, ionic solids have pretty high melting points because they have strong bonds. And interestingly enough, water can break up the bonds. When it breaks up the bonds, it encapsulates the ions like this, and helps stabilize it. All right, so we get the solution there, the blue solution. Concentrated means lots of solute. Dilute means a little bit of solute. Most people are familiar with these terms here. Concentrated. You can see that as far as the color goes, this is a much lighter blue liquid or blue solution than this. So this is much more dilute. This is much more concentrated. What happens is they put some copper wire in silver nitrate. What occurs here is the silver deposits as the metal. So this white crust that's forming on the copper is silver. And the copper is being eaten away to form copper 2 ions in solution. This is actually a single replacement type redox reaction in which we form copper 2 nitrate and silver metal. The silver metal is growing here. Silver likes to form these dendritic crystals, sort of branched crystals you can see here. So these are just crystals of silver, and then the copper 2 chloride, or actually not chloride, copper 2 nitrate is in solution. It's one way to dissolve copper metal, but we aren't physically dissolving it, it's chemically dissolving the copper metal using silver nitrate as an oxidizer. And it's not the nitrate that's oxidizing in this case, it's the silver ions. You know, even though nitrate's a more powerful oxidizer than silver, it's silver ions taking the electrons from copper to deposit silver metal. Not the nitrate ions taking electrons from copper to form NO and NO2 gas. Why not? Even though nitrate's a more powerful oxidizer, why doesn't it react in this particular reaction, this redox reaction? Somebody know? When we look at the redox chart, what's a stronger oxidizer, silver ions or nitrate? You can look at the redox chart. What's a stronger oxidizer, silver ions or nitrate? What's going to oxidize the copper to nitrate? So why isn't nitrate? Why aren't we forming bubbles of gas?
Because there's no hydrogen.
Yeah, because there's no acid present. We need the acid and the hydrogen ions present there. This is no acid present. Then nitrate gets reduced in rain, so silver. Without the acid there, it makes a huge difference, reactivity. And so that's why, in this case, silver ion would be the best oxidizer, copper would be the best reducer. Reaction between silver ions and copper. These are some terms that we use when we're dealing with solutions, and that is solubility. Solubility has two definitions. One is a qualitative definition. Is it soluble or is it not soluble? You know, chlorides, bromides, and iodides are all soluble, except for silver, lead, mercury. Right? Nitrates, chlorates, acetates are all soluble. Phosphates, carbonates, and chromates are all insoluble, you know, except for group 1 and ammonium. And so we use it qualitatively there. That's definition number 1. You know, will it dissolve or won't it dissolve? Definition number 2 for solubility is how much. This is definition number 2. How much solute dissolves? I don't want to know if it's soluble or not. I want to know how much dissolves. And typically what's done is you take 100 milliliters of water and you figure out how many grams will dissolve in that. That's what we call solubility. So if you take 100 milliliters of water and you take table salt, sodium chloride, all sodium salts are soluble, right? But it's not infinitely soluble. For example, if you take 100 milliliters of water, we can only cram 36 grams of table salt. If you try to put 37 grams, then 1 gram won't dissolve. You know, it's not infinitely soluble. And so the solubility is how much. For some things, you know, it's quite a lot. For other things, there's a limit, there's a finite limit. Sometimes it's infinitely soluble. Something that's infinitely soluble has a name. Does anybody recall the name? It's like methanol and water. Anybody recall the name when something's infinitely soluble? It has no solubility limit. It starts with an M. It's called miscible, M-I-S-C-I-B-L-E, miscible. And so if something's miscible, then there's no limit, but most things have some kind of finite limit. You know, you can only dissolve so much, and that limit varies. You know, for potassium chloride, it's different than sodium chloride, even though both are soluble. A saturated, this is what happens at the limit. At the limit, we form a saturated solution. A saturated solution you just can't get anymore. You know, once you reach 100% relative humidity, can you go higher? Can you go 200% relative humidity? Have you ever heard of that? You know, it's like, okay, give 100% of your effort. If you give 100% of your effort, you you should have 0% left, right? Although some people might say give 200% effort. But there's a limit. And that limit is when it becomes saturated. When it becomes saturated, you can't dissolve anymore. So if I take 100 milliliters of water and dissolve 36 grams of sodium chloride, it's saturated. It can't take anymore. If I try to stuff in 1 more gram, it can't. It won't take it. However, if it's unsaturated, we haven't hit that limit. So an unsaturated solution has not hit that limit. Sometimes you could have more than 100%. If you have more than 100%, it's called supersaturated. It's unstable though. You know, it cannot be sustained. We'll talk about that in just a second. Supersaturated. Usually supersaturated solutions are formed one way, and then you move them to conditions. So for example, at high temperature, are things more soluble or less soluble at higher temperature? Typically more soluble. So you could dissolve more sugar in hot coffee than cold coffee. Did you know that? You could dissolve more sugar in hot coffee than cold coffee. And so things tend to be more soluble at higher temperature. If they're gas solutes, then it's a different story. You know, for fishes, you know, they rely on oxygen dissolved in water. Is there more oxygen at high temperature or less oxygen at high temperature dissolved in water? Turns out there's less. If you have, let's say you have sparkling water, what happens if you heat it up? Will you get more bubbles or less bubbles if you heat it up? You get less, it'll go flat. And so for gases, it's the opposite, but for most everything else, it's more soluble. So what happens is if you have something that's hot and you cool it down, sometimes what happens is crystallization. You know, to form a crystal, everything has to be perfectly aligned. And sometimes things don't get perfectly aligned, and so there's a delay. And that delay of crystallization causes supersaturation. What does miscible mean? Not just soluble, it means infinitely soluble. What does immiscible mean? It's the opposite. It means it's totally insoluble. It has no. And so we'll take a look at supersaturated solutions here. For example, if we have a solution of sodium acetate at high temperature, you could dissolve a lot of sodium acetate in water at higher temperature. And when you cool it down, the crystals, you know, have a hard time forming because the sodium ions and the acetate ions have to be perfectly aligned to form a lattice. And if they don't perfectly line up, it's hard to form a lattice. And so what happens is there's a little delay. They should have shown this before. What they have here is a supersaturated solution of sodium acetate, and it's not sustainable. There's too much sodium acetate dissolved in water. But the problem is the crystals are having a hard time forming. And so what they're doing is they're adding something called a seed crystal. A seed crystal helps promote crystallization by providing a template for the crystals, new crystals to form. So they drop a seed in here, and then new crystals can form based on the template of the seed crystal. And so what you see here is that crystallization takes place, and all that excess crystals come out. And so this is supersaturated. We have to provide, this is called a nucleation site, a site where crystals can nucleate from. Now, let's take a look. It's probably better to see this as an animation. Supersaturated. The reason is when you look at the acetate ion, you know, what is the shape of the acetate ion? So when we look at acetate, which is C2, H3O2 minus. You know, on one end we have what? We have the CH3 group, which is, what's the shape of this CH3 group here? Is that tetrahedral. And then when we look at the acetate part of this, I'm going to draw it like this. There are actually two resonant charms to it. Negative charge there. You look at the shape of this carbon. What is the shape of this carbon? Trigonal planar. And so it's got a weird shape to it. And so when you put this in a crystal lattice, you know, those acetate ions have to line up correctly. And so this is why sodium acetate is the classic example of supersaturation. So let's take a look at the sodium acetate crystal lattice. You see how the acetates have to kind of, actually, are those, this is mercury. This is mercury 2 acetate, but it kind of shows the same thing. Do you see how the acetates have to line up? These are the acetates here. The acetates have to properly line up in the lattice, and then it can crystallize. Well, because of its shape, it doesn't line up so easily. So this is what a crystal of sodium acetate looks like. It forms very nice crystals like these long needles here. So we can see what the supersaturation is here. Let's try this one. Right now, basically what they did was they heated it up, and then they dissolved it, they saturated it at high temperature, and then they let it cool down slowly. When it cools down slowly, it should crystallize, you know, all the excess crystals that had dissolved, but it's not because it's having a hard time nucleating. So they're going to drop a seed crystal in here. So the seed crystal is going to help nucleate and allow the crystals to grow. So there. You see that little crystal there? They dropped in there. There. And so then, now the crystals can grow. They have way too much sodium acetate in there. That was not sustainable. And so all that excess sodium acetate that they had in there crystallizes out. Let's see. This is another common technique to help try to crystallize it out. Supersaturated sodium acetate. Just see. So there's the supersaturated sodium acetate, and this is a C crystal. Yeah, there's a C crystal on the bench top. And so it's just going to pour the solution on top of it. This is not like, it's not like hot sodium. This is back to room temperature. That's room temperature sodium acetate. And it's not freezing there. these are just excess sodium acetate crystals coming out of the solution. So there's a huge difference in the solubility of sodium acetate at room temperature versus a higher temperature. So this is just a pillar of sodium acetate. There. Yeah. All right, let's fast forward that. This is a seed crystal in a beaker here. Again, just showing crystallization. There's so little water, so much sodium acetate.
Is that a solid?
It's a solid, yeah. A solid sodium acetate. This water there, so this water just got incorporated into the crystal. That's other examples of supersaturated solution. The other example is you see Mentos and Diet Coke. Let's just do this. This is another example of a supersaturated solution, and that is the amount of CO2 that gets dissolved in this depends on how much pressure of CO2 there is in here. And so what they have in here is, in an unopened bottle of soda, is 1 atmosphere of CO2 in here, versus air. In air, the partial pressure of CO2 is like 0.03 atmospheres or something like that. And so we're going from 1 atmosphere to 0.03 atmospheres, which means it's going to be a lot less soluble. So you don't force as much CO2. And so this is another example of supersaturated solution here, which is this. And so the bubbles are coming out because there's too much CO2 dissolved in there, but you could speed this up. Speed it up by giving it a nucleation site here. So it's the same kind of thing as the seed crystals, just providing a surface for the bubbles of CO2 to form here. It's not Alka-Seltzer. You know, Alka-Seltzer would be an acid-base reaction generating CO2 as well. This is just Mentos candy. So here. So now this is supersaturated because all of a sudden when he removed the lid there, it was 1 atmosphere of CO2, removed the lid, now there's air getting in there. Air has very low partial pressure of CO2. There's way too much CO2 dissolved in here that can be sustained. However, the bubbles form slowly, and so to speed up bubble formation, you could use Mentos. That helps nucleate. So let's see what happens here. So that rapidly speeds up nucleation. And so here is just providing surface. We have these things called boiling chips. Did we use those this semester? Boiling chips? This is the same kind of deal. Boiling chips provide surface for bubbles to form, bubbles to be promote smooth boiling. Okay, here, miscible, what does miscible mean? Yeah, pretty much infinitely soluble. You know, they mix in all proportions. Immiscible means they don't mix. So things that are miscible would be things that are very similar. So for example, octane and carbon tetrachloride, they have no problem mixing together because they're quite similar in their polarity. Both of these are non-polar. However, octane and water don't mix. You know, octane is non-polar, water is quite polar. Methanol and water would mix, however, methanol can hydrogen bond with water. So methanol is very water-like. So methanol is miscible. Ethanol is miscible in water. And so here's miscible and immiscible. They mix, they don't mix. All right, when we look at formation of a solution, we have to look at the solution process, dissolving solution. So we can look at it here. So what this is showing is this crystal of sodium chloride here, and the water molecules, and then the solution over here. And so what has to happen is the crystal lattice has to break apart. The ions have to come off the surface. And the water molecules must make room for it. And so a lot of people think of this as a three-step process. One, the solute particles, we have to dissociate them or break them apart. Two, we have to break apart the water molecules to make room for the solute. And then three, we form solute-solvent spheres, hydration spheres like this, or solvation spheres like this. And so when we look at it, we have to think in terms of how strong is the lattice. If the lattice is very strong, it's going to be hard to dissolve. That's why like phosphate carbonate lattices are very strong compared to like chloride lattices, nitrate lattices. Why? Phosphate carbonate lattices are a lot stronger lattices than nitrate acetate. More charge, yeah, more polar. Higher the charge, like if this is -3, it's much harder to pull that ion off the lattice. And then we need a polar liquid, because what pulls these ions off are the polar water molecules. If we had non-polar liquid, it's not going to be very effective. Only collisions would do it. And then we have this. This is called an ion dipole intermolecular force. We have an ion which has a full charge and a dipole which has a partial charge. And so ion dipole attractions can be quite strong. These are ion dipole attractions here. So this is called the solution process. This is dissolving ion solution. For molecular stuff, it's the same thing. We have for molecular solutes, we have a rule. It's called like dissolves like. So nonpolar likes nonpolar. Nonpolar does not like polar. And so polar likes polar. So we've got a polar and polar works. And so like dissolves like. Ions are quite polar, they're monopoles. Ions have a big charge. Water's polar. This is it here. So this is the solution process. The solution process is dissolving the sodium chloride to form the aqueous ions we saw there. So we got to break apart the lattice and then break apart the water and then form these aqueous ions. The aqueous ions are those hydrated ions. There's a limit though. The limit is when we saturate it, we can only put about 36 grams of sodium chloride in 100 milliliters. Then it becomes saturated. When it becomes saturated, a dynamic equilibrium has occurred. The dynamic equilibrium is once this becomes saturated, then will more crystals of sodium chloride dissolve once it becomes saturated. Once it becomes saturated, then I can't dissolve anymore. It's full. It can't take anymore. And so we've reached this state of equilibrium. But why is it called dynamic? It's called dynamic because of this. The forward process is called dissolution. The reverse process is called crystallization. It's because dissolution never stops and crystallization never stops. The crystals are always going to be broken apart, but at the same time, crystals are always going to be forming. And so once we've hit this state of dynamic equilibrium, this is what's happened. So let's say we've saturated this. We've saturated this in this no more. If it's unsaturated, then we'll dissolve this whole thing. But if it's saturated, we add another crystal of sodium chloride in here, it's not going to dissolve. But at a atomic level, it does dissolve. What happens is that, we can't stop these waters from colliding here and knocking ions off. Can you stop that? No. There's going to be kinetic energy at room temperature. And some of these water molecules will have quite high energy that knocks off the ions. But if it becomes saturated, what happens is these ions can strike the surface and stick. If the ions strike the surface and stick, that's called crystallization. And so in a dynamic equilibrium, what's happening here is dissolution and crystallization is just going in circles. That's the dynamic part. So dissolution and crystallization never stop. The equilibrium is that there's no net dissolution and there's no net crystallization occurring. Hit this state, or you've seen a dynamic equilibrium before. What was that? Dynamic equilibrium you saw before. What's that?
Gases?
Yeah, it's with humidity. Once you hit 100% relative humidity, the air is saturated with water vapor. Will water still evaporate? Yes, but at the same time, condensation is occurring. So the evaporation and the condensation rate are equal. And so if you imagine this as a gas and this is liquid water, then when we saturate the air here, then evaporation doesn't stop. Evaporation continues. It's just evaporation rate is equal to condensation rate. We have a circle going on. We're just spinning but not going anywhere. This is the same thing. When we have an unsaturated solution, we can dissolve the solute. And so we get net dissolution. As we build up the concentration of solute here, some of the solute can go back and strike the surface here and stick. That's called crystallization. So dissolution and crystallization. But here we have net dissolution, here we have net dissolution. But once we saturated it, then the crystallization rate is equal to the dissolution rate, and nothing appears to happen. This is at equilibrium. But it's a dynamic equilibrium because dissolution never stops and crystallization never stops. And so even though you aren't dissolving, you'll see the crystals changing because there was a crystal there, but it's gone now. It's been replaced by a new crystal, kind of thing. So the crystals are always undergoing change, but the net amount of crystals doesn't change. Factors that determine solubility. Now this is solubility. The factors are the strength of the intermolecular forces within the solute, solvent, and in between the solute and the solvent. So, how strong is that solute? Does the solute want to break apart and go into water? How strong is the solvent? Does the solvent want to break apart and allow those? And how strong is the solute-solvent interaction? That's going to. Sometimes the solute's too strong. Like magnesium oxide. Magnesium oxide, that lattice is too strong. So it's insoluble. Calcium phosphate, insoluble. Calcium carbonate, insoluble. But sodium chloride, soluble. But this also goes for, not just solid salts like that, but it also goes for liquid. Here, gasoline. To dissolve gasoline or octane, those are actually, gasoline is a mixture of hydrocarbon. To dissolve this gasoline in water, the water has to make room for it, which it can. Water will make room for these if the interaction between gasoline and water is favorable, but the interaction between gasoline and water is not that favorable because it's just dispersion forces compared to hydrogen bonds. So water would rather hydrogen bond with itself than have dispersion or London forces or instantaneous dipole forces with gasoline. So it doesn't make sense for water to allowed in. Whereas for octane and carbon tetrachloride, it doesn't matter because the interactions are quite similar. Another thing is if we're dealing with gases. Now, gases we have to treat a little differently. Gases is a liquid solvent. What makes it a big difference is the partial pressure. The more CO2 gas there is, the more that's going to be forced into. The higher the pressure of the CO2, the more that's going to be forced into the liquid. And so if you have CO2 at 1 atmosphere, that forces a lot of CO2 into the water. And then all of a sudden, if you decrease that, you're going to have a lot less CO2 in water. And that's just what we saw here. Right now, we have a high pressure of CO2 here. The high pressure of CO2 is just 1 atmosphere, but it's pure CO2. What's in this, the head space here is pure CO2. That's a high pressure compared to air. What's the pressure of CO2 in air? Do you know? So if we have pure CO2 in there, that's 1 atmosphere of CO2. And so if we look at the pressure of CO2 in air, this is 0.3 outside air. And outside air is 0.3 torr. It's like 0.03 atmospheres, something like that, around there roughly. And so we go from 1 atmosphere to 0.03, we make a huge difference. Huge difference in solubility. And the temperature. Temperature impacts things. If it's a liquid and solid, increasing temperature increases solubility. But if it's a gas, increasing temperature decreases the solubility. So here's just another example. Ethylene glycol is quite polar. You see all the hydrogen bonds, the OHs here. So ethylene glycol is an alcohol, and alcohols can hydrogen bond with each other. But if you add oil to it, the oil doesn't want to mix. And so oil is non-polar, water is polar. Light dissolves light. So they don't mix. Ethylene glycol likes water. There's no problem with dissolving ethylene glycol in water. Ethylene glycol is called antifreeze for cooling. Here's partial pressure and solubility. The higher the pressure of the gas, the more gas molecules or particles are forced into the liquid. And so at lower pressure, we have a lower concentration to saturate. A higher pressure, we have a higher concentration to saturation. So the solubility increases with pressure. Here's temperature. So for most things, as the temperature increases, the solubility goes up. For most things. Some things, the solubility actually goes down, like lithium sulfate. But for most things, it goes up. This is what should happen. Ammonium chloride is dissolved in warm water, and what we have here is saturated ammonium chloride. All the ammonium chloride is dissolved. And then when they cool it in the ice bath here, well, as they cool ammonium chloride in the ice bath, the solubility goes down. Any excess crystals here will have to precipitate out, which is exactly what they do here. It's just with sodium acetate, it's hard to form the crystals, but with ammonium chloride, it's a lot easier. Ammonium spherical, tetrahedral, chloride spherical, so it's easier to line up those with crystallization. All right, those are some factors affecting solubilities. Now let's take a look at the composition of mixtures. The composition of mixtures we can give as mass ratios. Mass ratios would be like 50 grams over 100 grams, 50 grams of solute over 100 grams. So 50 to 100. That would be, in percentage terms, 50 over 100 would be 50%. We do 50 grams over 100 grams, 50 grams of solute over 100 grams total times 100%. The total is the solute and the solvent combined. So there's different ways of expressing it. So percent by composition we're talking about. Let's look at an example here. When 125 grams of the solution was evaporated to dryness, 42.3 grams of solute was recovered. What was the percentage concentration of the solution by mass? So in this case, there's 42.3 grams of solute over 125 grams total. So the mass ratio would be 42.3 over 125, and then times 100%. So it's just mass of solute, 42.3, over the total mass, 125. Take the mass ratio times 100 to get a percent. We do the same thing. It doesn't have to be, percent is for high concentrations. It could be part per million for lower concentrations. We take mass ratio, times it by million ppm, or billion for parts per billion for low concentrations. But for fairly high concentrations, we use percent. You are to prepare 2.50 times 10 squared grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? Density of water is 1.00 grams per milliliter. And so 7.00% by mass, well, the first thing is, what is that percentage? Well, it's 7.00 out of 100. So 7.00 watt out of 100 watt. Yeah, so this would be 7.00 grams of sodium carbonate per 100 grams of what? Yeah, sodium carbonate solution of the total. Okay. So we can use this as a conversion factor here. And so what we're given is, we're given 250 grams of solution, sodium carbonate solution. And so we can just multiply it by this conversion factor. Grams of sodium carbonate solution cancel, it leaves us with grams of sodium carbonate. So it would be 7 times plus 7 would be 14 plus 2, 3.5, 17.5. For every 100 grams of solution, we have 7 grams. We have 250 grams of solution, so I mean 7 plus 7 plus 3.5. Or we just multiply it out in dimensional analysis. All right, that's how many grams of sodium carbonate. Now, how many grams of water do we need? Well, we're going to have 17.5 grams of sodium carbonate and 250 grams of solution. And so the difference will be water. So that's what they're going to do next here. So they're just taking the 250 grams total minus the 17.5 grams of sodium carbonate solute, which gives us 233 grams of solvent, which is water. And so the grams of solvent plus the grams of solute equals grams of solution. How many milliliters is that? Well, at 1.00 grams per milliliter for water, that's 233 grams would be 233 milliliters. That's the 3 sig figs. If I wanted to more sig figs, then I'd have to look up the density of water. so you take 17.5 grams of sodium carbonate and mix it with 233 milliliters of water, and you should get 250 grams of solution. Percent by mass is common. Also, molarity is common. Molarity is very useful when we have to do stoichiometry, because we can do direct liters to moles conversion here. Liters of solution to moles. Liters of solution is easy to measure. Anyway, molarity is defined as moles of solute per liter of solution. Calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide and diluting it to 1.00 times 10 squared milliliters, so 100 milliliters. So we're going to take 15 grams of sodium hydroxide. We're not going to add 100 milliliters of water. We're going to add enough water to make it the total volume. So this is the volume of the solution, 100 milliliters. And so the molarity is the moles. We'll need the moles of sodium hydroxide, so we'll have to do a gram to mole conversion, divided by liters. So we're going to have to convert from milliliters of solution to liters of solution. The first step is to figure out how many moles of sodium hydroxide. The molar mass of sodium hydroxide is 40.00. So 15 divided by 40 gives us 0.38 moles of sodium hydroxide. And then we're going to divide by the liters of solution. Well, 100 milliliters is 0.100 liters. So 100 milliliters is 0.100 liters. So we'll just take the moles divided by the liters of sodium hydroxide solution. That's going to give us the molarity. Comes out to 3.8 molar sodium hydroxide. 3.8 moles of sodium hydroxide per liter, or 0.38 moles per 0.100 liters. That's molarity. There's one more you should be aware of, it's molality. Molality is defined differently. It's the solution composition based on moles of solute per kilogram of solvent. Per kilogram. The advantage of molality is molality doesn't change with temperature. Molarity does change with temperature. Because what happens is the density changes with temperature. Certain liquids expand and contract with temperature. If the liquid's expanding or contracting with temperature, that's going to change the liters, which changes the molarity. However, kilograms won't change, with temperature. So if we have 1 kilogram at hot temperature, it'd be the same 1 kilogram at cold temperature. But if we have 1 liter of liquid at hot temperature, it'll be a different volume at cold temperature, because liquids and solids tend to contract at colder temperatures. That is, shrink. And so molality is useful in the sense that it's temperature independent, but it's not very useful for stoichiometry because we need the density. We'd have to measure the density, and the density changes with temperature as well. How many grams of potassium chloride must be dissolved in 250 grams of water to make 0.400 molal solution? And so, what is 0.400 molal? 0.400 molal is 0.400 moles of potassium chloride per kilogram of solvent, kilogram of water. And so if I have 0.400 molal potassium chloride, KCl, that's equal to 0.400 moles of KCl per kilogram of water. It's not solvent. I mean, it's not solution. It's only the solvent. And so it's weird. Well, that's okay because we're given the solvent, 250 grams of water, that's the solvent. And so this is just dimensional analysis. Dimensional analysis is, we'll go from 250 grams of water to kilograms of water. And then if we know how many kilograms of solvent we have, then for every kilogram we'll need 0.400 moles. So this is 250, so it'd be quarter, 0.25. So we'll need 1/4 of that. Should be about 0.100 moles, and then, so that'd be about 7.5 grams or so. There's a molar mass of KCl, 74.55, about 7.5 grams to 2 sig figs, 7.46 to 3 sig figs. Again, these slides aren't consistent with
I
the sig
think
fig.
the 1 kilogram over 1,000 grams, is that like a thing that you know, or?
Yeah, this is just memorization. 1,000 grams in a kilogram, 1,000 milliliters in a liter. You know, it's just memorization. 1,000 meters in a kilometer, and so it's kilo.
So why are we converting it to kilograms?
We're covering it in kilograms because of the definition of molality. Molality is moles per kilogram.
So we can use molarity for that?
No, not this particular problem. The molality is given the little m. And since we give that, we can do a conversion. We can convert molality to molarity, but we would need the density, which is not given. And so I can tell because the little m means molality. Normality, we're going to skip it. Normality is, if you do a lot of titrations, you might use normality. So skip normality. And so the ones we do are percentage, and percentage is part per 100. We can also do part per million, part per billion, part per thousand, whatever. Those are all mass ratios. We've got a small mass ratio, we might want to use a ppm or ppb. If we've got a big mass ratio, we'll use a percentage. We have molarity. Molarity is defined as moles of solute per liter of solution, and we have molality, the little m, which is defined as moles of solute per kilogram of solvent. We have normality, which we're going to skip that entirely. When you buy soaps and detergents, usually you try to buy the concentrated stuff, right? Usually you try to buy the, and if you buy the concentrated stuff, well, then you dilute it. And so you buy the concentrated stuff because it saves you on shipping or whatnot. But we don't want to use it. Like, you usually do a dilution, like a 10-to-1 dilution or whatever. And so if you buy concentrated and then dilute it, so this is before and after, we're just adding water. So here we have the solute, 1, 2, 3, 4, 5, and the water. And then we add more water, we dilute it, and we still have the same amount of solute. So the moles of solute doesn't change. The moles of solute or moles of solute after don't change. So we have something called the solution dilution equation here. The liters times moles per liter gives us moles. The moles in the concentrated is equal to moles in the dilute, the number of moles. In other words, it's the volume of the concentrated times the molarity of the concentrated is equal to the volume of the dilute times the molarity of the dilute. I just call this like V1M1 is equal to V2M2, where 2 is the dilute and 1 is the concentrated. So we can predict, we can do the calculation based on the dilution factor. Talk about this here. Typically, we're interested in the molarity of the dilute solution. And so the molarity of 2, the dilute solution, is equal to V1 over V2 times M1. And so this is the dilution factor. So if there's a 1 to 2 dilution, you take 1 part original and dilute it to 2 parts, then the concentration is going to be cut in half. It's a 1 to 2 dilution. So if we take 1 part here and dilute it to twice, that would be a 1 to 2 dilution. And so the concentration would be about half. This looks like a little more. This looks like a 1 to 3 dilution. 1 part original, 3 parts final. Does that look about a 1 to 3 dilution to you? So if it's a 1 to 3 dilution, then this concentration will be 1/3 the original, because the dilution factor is a 1 to 3. 1 to 3 dilution. Let's look at this dilution here. They have 100 milliliters original, and then they're diluting it to 1,000 milliliters. So it's going to be a 100 milliliter to 1,000 milliliter dilution. And so the dilution factor is this. The dilution factor is going to be 100 over 1,000, or a 1 to 10 dilution. If it's a 1 to 10 dilution, then the final concentration should be 1/10 the original concentration. And so if the initial concentration here is 0.100, then the final concentration is going to be 0.0100. Does that make sense? The 1 to 10 dilution. That's what they're doing here. Now, how do you do a 1 to 10 dilution? So if I want to do a 1 to 10 dilution, I take 1 part of this and dilute it to a total of 10 parts. And so the way you do it is this. You put 1 part of this in, and then how many parts of water? 9 parts of water, right? If you put 1 part of this and then 9 parts of water, that gives you a total of 10 parts. But because of the way liquids mix, we don't put 9 parts of water. What we do is we'll just keep adding water until we hit the 1,000 milliliter mark here. And so I'm not going to fill this one up 9 times and then dump it in there. I'm just going to take 100 milliliters. This is what we call a volumetric flask, and there's a line here that marks 100 milliliters. I'll dump 100 milliliters in here. However, I didn't get all of it, so they're going to wash the rest of it in there. Once you wash the rest of it in there, then you're going to fill this flask up to the 1,000 milliliter mark right here. And so we'll add enough water to dilute it to 1,000. So we're going from 100 to 1,000. This is a 1 in 10 dilution. How many milliliters of commercial hydrochloric acid, which is 11.6 molar, would you use to prepare 5.50 liters of 0.500 molar hydrochloric acid? And so in this particular problem, what I would do is I just do this. M1 is 11.6 molar. This is the concentrated stuff. Okay, V1 is what they're asking for. How many milliliters of this concentrated stuff do I need to prepare M2? M2 is what I want to prepare, 0.500 molar. And V2 is how much I need. I need 5.50 liters of this. And so I want 5.5 liters of 0.500 molar. I'm going to start off with 11.6 molar. How much of this how much of the concentrated stuff do I need? And so V1 is going to equal M2 over M1 times V2. So if I look at M2 is 0.500, and then M1 is 11.6 times V2. V2 is 5.50 liters. And that should give it to me. I'll just need a fraction. I don't need all of it. I just need a fraction of the original concentrated stuff. And so this is the fraction of this concentrated stuff that I need to prepare this. What is that fraction? 237 milliliters, or 0.237 liters. And so the volume comes out to 0.237 liters, which is the same as 237 milliliters. Just move the decimal 3 places over. So this is the fraction here of the concentrated stuff. So what I do is take 237 milliliters of the concentrated stuff and then add enough water to make it 5.5 liters. Okay, let's stop here. We'll take a break and then finish up this. Do the break.